You know what? I watched that video of you. You remember last year? Oh, I laughed. Okay. Right. So I'm going to say this again. What do you need to know here? You need to know when it's at the vertical, there is no interaction between the magnetic fields. So the EMF, the volts that is produced, is 0. And when it is horizontal, then it is the maximum and the minimum. Okay, right. So what they can do is they can give you a picture like this and ask you to draw the graph. Or they can give you the graph and say in what position, horizontal or vertical, is the armature or the coil at B. Then you must say it is horizontal. Okay, so you must be able to connect those two ideas with one another. Okay, now let's read it. It says, because the current changes direction, so it's positive and then negative, positive and negative. Ma'am, where did we do that? We did it here. Okay, we saw that the current changes direction. So because it changes direction, it is called alternating current, AC, alternating current. Now, where do we use alternating current? We use it in cars, alternators or dynamos that supply electricity to recharge the battery and direct electrical energy to the components. Okay, so when you start your car, you hear, right? There's something that starts to turn. That thing that starts to turn starts to generate electricity. And then when you switch on your lights, you have lights. When you play your radio, you have radio. When you want to wipe wipers, you have that. Okay, so that thing in your car turns and it generates electricity for all of the stuff that needs electricity in your car. Then also, it's not a use, it's where we get it. ESCOM delivers alternating current, and then obviously we have emergency generators when ESCOM doesn't work. Right, now the advantages of alternating current, it is very easy to generate. It's much easier to generate alternating current than it is to make batteries. Okay, batteries are also more expensive. Then the transformers at ESCOM uses alternating current, so that's quite good. And then electrical appliances uses alternating current. So electrical appliance is something like this heater, or your microwave, or your kettle, or your iron, or whatever. Okay, so how do you know it uses alternating current? Can you see a box from the plug? Wait. Can you see a box from the plug to the thing? No, so there's nothing that changes it from alternating current to direct current. So this thing takes direct alternating current because there's nothing that changes it. Whereas my digital appliance, this thing here, has, if you look at it, it has a converter that changes it from direct alternating current to current. Okay, right. Then disadvantages from alternating current. Okay, so there are a few disadvantages. Number one, digital appliances only use direct current. So your laptop, your cell phone, your digital appliance. Then, every time the current changes direction, then self-induction occurs and causes some of the electrical energy to be wasted. Okay, right. Now, I think most of you have swam in a swimming pool or a dam or a river. Yes? Okay, and when you have done that, or a big bath, and you go, say there's a small, like a cement dam. Have you seen those things? There, that the farmers use with the pump, right? Now, can you imagine if you swim around, round, everyone, there you are 5 people in there, and you swim around. Then a current will start to form, right? And then you can just stop and you can float with the current and you go around. Or when you want to play, you say, okay, we go around and around, and then you say, okay, everyone turn around and we swim the other way. Yes? No? Can you imagine? You've never done that? Oh, you must do this weekend. No, this weekend will be cold. Don't do it this weekend. Alright, but can you imagine that if you put your hand in a basin and you go around like this, and you want to try to go the other way around, it's more difficult. Okay, now it's the same thing with alternating current. So all the charges go speedy fast to this side, and then the current changes direction, so then they must go back this side, and then they must go back this side. So every time change direction, there's still some current, some momentum coming in the opposite direction. So they first have to overcome that current before they can go in this direction. Then they have to change, now they have to overcome this momentum before they can go in that direction. Can you imagine it? Okay. So because of that, we call that self-induction. Okay. And it causes the current to lose some energy because it must first overcome its own momentum. Okay, right. So the result of this is that appliances effectively receive a lower potential than the peak valued supplied, or you can say the maximum value supplied. Okay, so that just means ESCOM promise you 240 volts. And if you have a reader at home, you'll see you don't get 240 volts. You get 220, 180. Okay, so you get much, much less. Why? Not because ESCOM tries to cheat you, but because of self-induction. Sometimes because of ESCOM, but you know. Right. Then that lower value is called root mean square value. That's the name of it. Root mean square value, and we use the abbreviation, and you're allowed to use the abbreviation RMS, root mean square value, and that is equal to its direct current equivalent. Its direct current equivalent. Okay, now I want to mention a few things here. Number one is in your exam guidelines, there is the definition for that you need to know. Okay, they've asked you twice in past tech papers, so you need to know the root mean square definition, and it's in your notes. It's more or less this bullet point there. The result of this is that, what is the definition? But I think it's this one here that I made the definition. Okay, anyway, then if you look on your data sheet, do you have your data sheet here? If you have, take it out, please. If you can share with the person next to you, that will be very kind. Okay, right. If you look on a data sheet, not the grade 11 data sheet and not the chemistry data sheet. Okay. On your data sheet, there is a section that says alternating current. Okay, right. Then there are a few formulas, and I'll get to those formulas in a second. But this here, we're producing current. Where else do we find currents? In circuits. So you can link these formulas with these formulas. Okay, so current formulas you can link with alternating current formulas. But very, very, very important. When you use the electrical or the circuit formulas, it must be, or you must use the root mean square value. Okay, so here you're not allowed to use the maximum volts or the maximum current or whatever. It must be that lower one after self-induction has taken place. Okay, so when you use, make a note for yourself. When you use R is V over I, or P is V times I, or energy is V I squared T, is that a formula? Near V, no square. Okay, when you use those formula, then it must be the RMS value, not the maximum value. Okay, why is that? Because if you plug in a light bulb or a buzzer or your microwave, you don't get the maximum volts or the maximum current. You get the root mean square volts of current, the lower one. Okay, and then here what I said here, I just want you to write down, the second thing is the root mean square is equal to the direct current. Okay, so those two ideas are linked. Okay, sharp. And then I just want to show you another thing here, is where we say a current has been rectified. So here you can see we have alternating current, and here we have direct current. Okay, so it's just been rectified. What does that mean? It just goes in the same direction. Okay, they can ask you to redraw that into that. Sharp. Okay, right, then you see here on the next page, I give you the formulas. Those formulas are all on your data sheet. So this just shows you how do you go from the maximum value to the root mean square value. Sorry, here it must say that's VGK is the Afrikaans. It must be RMS. RMS. All of them must be RMS. RMS. What happened here? COVID. RMS. Just blame everything on COVID. Okay. So gemiddeld in English is average. So the average is equal to volts times current. So these formulas, the bottom formulas, should look familiar to you. You've seen them before. Yes? Just without all of the footnotes. Okay, so they are all on your data sheet there. The two that is also on your data sheet, but that is new, is these two here at the top. That just shows you how do you go from the maximum that is promised to the RMS value. Okay, right. Then the next thing here that I just want you to show, you don't need to know everything on here. So you can see here we have the alternating current. Beautiful, beautiful. I want you to see there, the top part there is the peak value, or we call it the maximum value. And then the one that is just a bit lower than that, so after self-induction has occurred, that is the RMS value. Okay, so that is the only two things I want you to see. Let's look at how easy these calculations are. They are really easy peasy. So Nelly, yesterday you cried because you said, ma'am, this chapter is difficult. Was it you? Was it you? And is it still difficult? Okay, right. So it says the peak voltage delivered, or the maximum voltage delivered.
So what did you say the RMS value is?
RMS value is the lower volts. Or the lower current. Doesn't matter. Okay, the peak voltage delivered, or they say the maximum voltage delivered, maximum, is 360 volts. Right, then they ask you question A, calculate the RMS value of this current. Okay, this question will count 2 marks in a test or exam. So they give you the maximum, they want the RMS. There's one formula that takes you from the maximum to the RMS, and this is this formula, volts RMS as volts max over the square root of 2. So that is 360 over square root of 2. And we are at Karabu again. Two decimals. Good. And the unit? We're calculating the volts. Yes, V, volts. Okay, so it's not a difficult calculation at all. And how can you check this out that you're on the right path? The RMS must be lower than the max. Is that lower than 360? Yes, it is. Okay, right. Then at question B, they ask, calculate the average power. So we want the power. They say the resistance is 60 ohms. Now we have V max is 360. And we have VRMS is 254.56. Okay. Is there a formula that you can take resistance and volts to get the power? Kambu, if you check there at the top of the page. We have resistance, we have volts, we need to calculate the power. Here's that last one there. So P average, now when you write down these formulas, you want to write them down with their subscripts, their footnotes or whatever. V squared. Now can you see there that the formula requires you to use the RMS? You will always be required to use the RMS, never the max. Okay, so if they give you the max, you must first go convert it into the RMS and then you can use it in any other formula. Okay, so do not be tricked into using the maximum volts. It's 254 point. Okay, and Retabile is on it. He is quiet today and he's on it. What has changed in your life, Retabile? What do you get? 1080. And the unit? No, the unit? You're calculating power. What is power measured in? What? Huh?
What do you mean?
Yeah. What? W is watts. Okay, you guys are laughing now. I'm gonna laugh at you in the test. Okay, right. You rebuke it. Okay. Right, let's look at the next one. It says two identical bulbs, B1 and B2, are connected in two different power sources. Yes. Yes. Work is measured in joules. Power is measured in watts. Yeah, I know they're not the same thing.
So we should never use the Vmax.
Never use the maximum current, maximum volts. You first have to convert it into the RMS. Okay, so the next question. It says two light bulbs that you have at different sources. The one has a 12 volts direct current power source. So there you can see a battery. And the one is connected into a plug that tells you the maximum volts that you get is 12 volts. And the frequency is 25 hertz. That just means there's 25 waves per second. Hertz is the number of waves per second. Okay, so there's 25 waves per second. All right. Then they ask you there, which one of the bulbs will glow the brightest? We're going to do, sorry, I just want to split this up. So we're going to do, you can split this up in 4. Okay, so we will do A, or not in 4. Here we are. All right. So they ask you, which one of the bulbs will burn the brightest? You must remember, brightness is connected to power. Retabili, what is power measured in? Well done. Okay, so they want to know which one's power is the biggest, or which one burns the brightest. Katlego, which one do you say? B1 or B2? First one. Yeah, I know you're exactly that guy. Okay, it is B1 that burns the brightest. The next one, they say, perform a calculation to justify your answer, to say why does it burn the brightest. Okay, if we look at B1, it is connected to a DC, direct current. So no volts is lost. There's no self-induction that takes place. So the volts that it gets is 12 volts. It gets the total 12 volts. Whereas with B2, it is alternating current. So there is self-induction that takes place. So we first have to go calculate what is the volts RMS. What is the actual volts, the root mean square volts that it obtains, that it gets. So that is the volts max over the square root of 2. The maximum volts that it says was 12 over square root 2, and you get what? Beast.
8,49.
And the unit?
Volt.
Volts. Oopsie. Volts. So we can see effectively it only gets 8,49 volts. So it gets less volts. And thus it burns not as bright. Thus B1 is brighter than B2. Okay. Then in question C they ask, what is the ratio of power in bulb B1 versus B2? Okay. Now, ratio, what you do is you put it next to one another. So you say the power of B1 versus the power of B2. Okay, now to calculate power, there's a few formulas. I'm just going to write it down here. Power, you can say, is volt times current, or power is I squared times R, or power is volt squared over R. Okay, let's check for each of those two light bulbs. So I'm going to go back to my picture. I know now what the volts will be for this one, and I know what the volts will be for that one. So I have volts. So I have volts and volts. I know they say there are two identical bulbs. So I can take their resistance to be X, or I can take it to be 5, or I can take it to be 10, or whatever. It doesn't matter. Okay, they're just the same. So I have their resistance. Do I have their current? No. Okay, so that causes me to use the third formula, because I have the volts and I can compare the resistance because they are equal. Okay, so here we have volts squared over R, and here I have volts RMS squared over R. Why? Because B2 is connected to alternating current. So it doesn't have the maximum volts, it has less. Okay, now because the two resistance are equal to one another, I can just remove them because it's dividing the number by the same thing. Okay, so I'm going to take this just as 12 squared, and I'm going to take this as 8.49 squared. Those values we got at the top. Okay. Juvandra, are you on it? On calculating those two. Read the question. So we're comparing the powers. Jivandre, what you got for the first one? B1? No, not the ratio just yet. I just want if you type that into your calculator. What do you get? And the other one? 72.0. Okay, what do you do next, Zanele, to get a ratio? Can I just leave it like that? What do I do? How do you get the ratio? Yes, you're going to divide by the smallest number on both sides, and then you're going to go round up or down if you're close to a whole number. Okay, then you should get 1 to 2, more or less. Mary, please explain in words how the brightness of B1 will compare to B2. I'll say again, B1 will? Yes, B1 will burn twice as bright as B2. Or I can ask this as a multiple choice question, and they love to ask this as a multiple choice question. That is why I put it in here. They can tell you, okay, the brightness of B1 is bold P. You know those multiple choice questions where I say, consider let the brightness of bulb 1 be P. What is the brightness of bulb 2 in terms of P? And then I give you 2P, 4P, a half P, or a quarter P, or whatever. What will it be? Chabu? The brightness of B2. It will be a half. Okay, right. Then they ask you question D. Sketch a graph of voltage versus time for one complete cycle of an AC power source. Show the maximum value and your time max. Okay, right. So we are going to draw a graph. They do ask you to draw a graph quite often in the end exam. So you have time. Sorry? No, like this. No, man. So they'll say get the volts, or they'll say the induced EMF, or whatever. You must just know that's in volts. For one, they say here the question, I think it's one cycle. Yeah, one cycle. Then you're going to show it goes up and it goes down. And they say show the maximum volts, and we said that was 12 volts. I can also ask you show the RMS, the root mean square value, and then you're going to say the root mean square value was left, it was less 8.49. Yeah. Okay, so please listen carefully for homework. I know. Your homework is page 12. It's just a summary. So page 12, if you write more than 20 things, it's wrong. 20 words. Okay, so it's just, here's a summary. I ask you, with the electric motor, what do you start with? Electricity. A generator, what do you start with? Motion. Okay.